All right. It's 35. Welcome back. Everybody gets a million bonus points for coming when it's so beautiful outside today. Not really. I don't have a million bonus points. No, it's a really nice day outside. That's great. Okay, so last time we did a quick excursion into like the very big, thinking big, trying to think about robots running around the entire some big environment. But I want to dive back now down into some of the details of what's happening exactly at the level of the arm. This is, I think, maybe one of the last really core pieces that we haven't talked about in terms of the manipulation stack. Okay, so I want to think about interactions. Even when I write, when I write on the board, the interactions between my hand and the board are actually fairly subtle. And if I don't think a little bit about the amount of force I'm applying, for instance, then I could go and get into trouble. And robots, the old robots that were completely position controlled and very stiff would have had a hard time doing something like that. Okay? So let me motivate it a couple different ways. First of all, you actually don't need to do sort of think about interactions to already motivate this. So if you look at the failure cases from our clutter clearing example, I had my list of sort of different things that fail. This was one that cracked me up. I looked down at, I generated a bunch of random environments, and I looked down and I was like, okay, that's impossible. For our antipodal grasping strategy, the hand is not big enough. We got unlucky. The Cheez-It box just happened to land completely flat, right? And there's not going to be, it might try to grab it here, right, and not do very well, but there's really nothing that our antipodal pick-and-place strategy could do to clear that Cheez-It box out of the bin. The hand is too small for the box from that orientation. So when that one popped up, I actually asked my younger daughter, I said, what would you do? So I went and got a two-finger gripper from the kitchen, right? And I found a plastic box. We have plenty of them from Amazon. And just started asking her, what would you do to get that big box out of? And she did really clever, you would have probably done the same thing, right? But there's plenty of strategies available, okay? But they're more than pick and place, right? They required something else, right? And then she started doing it with her hand, and that's just not even cool. She deformed her hand sufficiently to open up the box and to completely power grabs the box. But okay, so I've been saying all along that manipulation is more than just pick and place. Okay, and this is maybe our first foray into it. Okay, so the things that are happening there have a little bit of grasping manipulation. The word you'll hear for that is prehensile manipulation. Okay. That means grasping. Okay, but there's a lot going on in that video that would be called non-prehensile manipulation. And that's all the other things that she did with her hand to move that box around that did not involve having a firm grasp on the hand. Before she got the grasp on the hand, she's applying forces on the side, regulating forces between the box and the sidewall, between the box and the bottom, accomplishing this sort of pivot maneuver. Then she could go in and do her prehensile manipulation. And I haven't really given you the tools yet to do that, but we're going to start today. Okay, so the classic examples of force control, and a point that I'll try to make once we see the math in a little bit, is that these tasks, I already alluded to it with writing on the board here, but these tasks are actually pretty old, right? There's a historical perspective of force-based manipulation written in '87, right? And the classic applications of worrying about force, even with a rigid manipulator, was to do things that involved contact with the environment. And in particular, if you wanted to do something like follow an edge, but you didn't have a computer vision system that was estimating the location of that edge or the geometry of that edge perfectly, this is actually not only edge following, it's actually blind edge following, okay? The force controllers we'll design today are actually going to be capable of, without any estimation of that curve, perfectly following the curve, okay? And that makes sense. We're going to go down until we touch, we're going to apply some force, and we're going to start moving sideways, and we're going to regulate the interaction forces, and that's going to keep me perfectly in contact with the edge without needing vision. Okay? Here's another time where you might need to think explicitly about regulating force. So we want to slide this book to the edge of the table so we can pick it up. There's some friction coefficient between the book and the table. There's some other friction coefficient between the hand and the book. And you need to push enough that you can move the book, but not so much that the book is in static friction with the table, right? And then you can slide it to the edge. Yeah?
So are there general multi-canceling patterns, or do you have to do them like things like this?
So there's a whole world of extending motion planning to planning these kind of maneuvers. You can also do reinforcement learning to get them. There's a handful of approaches we'll talk about to get these sort of planning through contact or control through contact. Yeah. Oftentimes, I would say that the tide is turning. I think it wasn't long ago where people would handcraft them, and we're starting to now replace those with, automatically generated. Okay, so that's a couple examples of maybe why we should think about controlling force. How many people have heard of impedance control? People understand the derivations of impedance control, right? I find, so we're going to go through impedance control today, but I find that after trying to teach it a few times, I find that the way I'm going to try is I'm going to take the simplest possible case, okay, and I'm going to go all the way through from position control, force control, stiffness control, impedance control, but I'm going to do it in the case of my robot is a point, okay? All of the details of the kinematics of my arm are going to just disappear. We'll come back to them and we'll do the same thing next time, and I think hopefully that'll just plug right in, okay? So the goal is to understand how to do these kind of tasks and to get to impedance control, but in the simplest case first. Okay, so here's my point finger manipulating the Cheez-It box, and I'm going to keep everything in 2D. Okay, so this is the same bin that we've been working with the whole time. I just sliced it down the side because once I constrain things to be in the plane, that doesn't matter, and now we can see inside the bin. I have a finger that's a point. That's my robot. Okay, a point robot with a point mass. Right? It's got some volume here for rendering, but I'm going to do all of my math with it being a point mass. Okay, and I'd like to do the kind of things that my daughter were doing to flip up the box by thinking about force control between the point finger and the box. Okay, so let's dive in to that example. So let's start off by just even thinking about free body diagrams for something like that. And I'll even start simpler. Let's just say the box is flat, okay? I've got my box. I should use my multicolored chalk capability. Okay, I've got my finger here, a little bit massive there, but let's do the free body diagram around the finger first, okay? So I actually wrote all this up with using F for the frame for the finger, which made a lot of sense. And then I looked back at what I'd written, and it's like forces of F, and there's just like so many Fs. So I'm gonna go with R for the board work here, and I'll fix the notes tonight. I was just looking at it like, wow, that's a lot of F's. So okay, so that's going to be robot R. Okay. So let's think about what's happening here. Okay, so there's two forces at work. There's the force of gravity, okay, and then there's the contact force that in the frame of the robot is going to be, let's say, a force like this in this direction, which we'll write as F of in the robot frame. Okay, the robot's a point, so I'll go ahead and call it at the center of mass of the robot R. Okay, and this is the contact force. So this is, if you remember our notation here, this is applied on body R, robot, at the point R here, and that's just the name, the contact. And that extra notation is going to be necessary today because there's a similar force, right, or the identical equal and opposite force sitting right there. If I were to write F of the body, which could be still at the point, evaluated at the point of the robot, which of course has got to be equal and opposite to the robot contact force.
Is the direction of that force correct?
What's that?
Is the direction of that force correct? Like,
The robot is experiencing a force that is keeping it out of contact, right? So it's going to depend. I mean, if I were to just have a robot with no forces being applied, then maybe you would say that it's just going to fall and there's no contact. But the only thing that this can be doing is pushing me that way, or friction, but it's not going to be pushing me that way. Yeah?
is that point approximating the mass of the cylinder?
Yeah, so I'm going to shrink my entire robot to a point, and I'm going to give myself fictitious force actuators that are allowed to apply forces at that point. But in practice, you could think of this as, what we're going to do next time is sort of fill that in with an entire robot that has an actual base and is achieving the same force commands by applying torques at the joints. Okay, but I'm going to abstract that away and say I could use these torques later to apply a force. Okay, so that's the one other force that could be involved then, is if the robot has actuators that are pushing it around. If I were to write the sort of force balance equations, if I was in static equilibrium, okay, then I would write that F of gravity applied on the robot plus the F of contact applied on the robot, everything in the same frame, plus my input commands, my actuator, let me call it actuator, effort here. That it's going to sum to 0. Okay. Now, one other note about this notation, just since we're going to build on it, right? So remember that I have a spatial force, gravity, that is composed of both the torque and the force, right? I've just used the little f this time, which is the translational components of the force, because the finger is a point, so there's really no need to worry about torques at this point. Okay, so a translational force is sufficient. There is no torque applied at the point finger. Yeah. We absolutely do consider the friction. That's part of the contact force. The total contact force. I drew it ideally sort of just pointing straight out, but it could be up, down. It could be anywhere inside the friction cone. Yeah. Oh, really? Which colors? The green? Okay. I will stop writing with green. Is there anything that you want me to rewrite? Yep. I mean, so there's a robot up there in green, but yeah, there's a green finger up there. Hopefully that's okay. If the robot is hard to see, that's okay. That's just an idea. That's only in our imagination, so it should be almost invisible. Yeah. In the frame of the body, in the frame of the robot, these are the only forces, right? So in order for the robot to not be moving, then absolutely, yeah. Well, always, even not in equilibrium, there's going to be an equal and opposite force applied to the body. So then there's also a set of conditions that must be true for the box to not be moving. These are conditions saying that the acceleration of the robot itself is 0. Yeah? Great. Okay. So let's say we want to actually, well, let me just manipulate this once before we do it. So if I were to rewrite that a little bit, I could say that the contact force, I could always solve for that. It's going to be the opposite of my whatever commands the actuator commands I was sending to my robot, and gravity, right? In the equilibrium configuration, the contact force is going to be, must be, in order for it to be in equilibrium, the opposite. So this is the simplest version now of force control. If you want to control the force you're applying on the robot, or on the box, right? If you wanted to not push too hard, or push very hard, or whatever, given this static equilibrium assumption, which is actually not a bad assumption. If we're moving super slowly, right, then it's actually a pretty good model, and we're going to use it often. Okay, but in that regime, then I could just decide, I can now solve what does my U need to be if I have a desired contact force, right? And it's almost, it's almost so simple that I shouldn't even write it again here maybe, but it's, if I have now a desired contact force, right? So I want to command my robot to achieve a certain contact force. Then what must I do? I must choose a U here that just basically cancels gravity and applies the proper force. So it's going to be F of gravity RR minus F of the contact desired. The hardest part about it is getting all the signs right because there's a negative U there and stuff, but okay. I think that's right. Does that make sense? That's just seeing it algebraically. But it turns out that's exactly the same thing that's going to happen even when we have a big robot there and we're going to run through more complicated equations. It's just doing exactly the same thing. In this case, it's canceling gravity, and then it's applying the force that it needs to do to apply that particular force. Okay, now there's a super important point I want to make here, which is that, so this assumed that we were in contact. What happens if I find myself in an initial condition? Remember the wall following example there, right? What if my finger's a little bit not in contact? And I'm blind. I didn't pay for a camera for my robot. Then what happens if I just naively apply this controller? Yeah. The finger's going to accelerate. In which direction? right? So that's intuitive, but let's make sure we see that. So if we're asking for it to have a contact force this way, and it doesn't get that contact force, then it's actually going to accelerate in that direction. So these simple force-based controllers are actually they tend to be very robust to not knowing the local geometry of the environment. Okay, so I could say that again. Let's just, in this particular case, the equations of motion are so simple. Right? They're just going to be F equals ma, right? This is ma equals sum of the forces. The forces are gravity plus u, and in the no contact case, I'm not going to have any contact forces here. So just think of the no contact case. Yeah. So I'm not actually making a static equilibrium assumption here. So that's a great question. So let's just understand what the accelerations would end up being if I applied that. So my controller design assumed static equilibrium, and now I'm going to ask what happens when I'm not in static equilibrium if I just applied that controller naively. And it turns out what happens is pretty reasonable, right? You basically, if you plug that in, you get mq double dot is negative of the desired contact okay, which means if I had a desired contact force like this, then what I'm going to find is that my robot is going to accelerate in this direction. And this is actually one of the reasons that people like force control a lot, right? So walking robot people like force control. A lot of times there'll be extra effort to put sort of force control either by sensing the feet or by having torque control in the legs, right? When you're swinging your leg forward, no big deal. In fact, people often use position control for that because they want to control where the foot placement lands. But as soon as you go into the mode of trying to be in contact with the ground, then you tend to try to use a force control if it's available on your robot. And that's precisely because you want to be relatively insensitive to the location of the ground. And it seems that animals probably do this too. There's kind of a classic video here. Okay, let me just set this up before I hit play. This is a guinea fowl, okay? It's being asked to run over and over across this platform in front of a high-speed camera. And then one day, they changed the environment a little bit, and it's visually the same, okay? But this is actually paper now, like really thin paper, okay? So this guinea fowl is going to be running along, and then the ground is just going to change. Its visual perception of the ground and the actual ground are going to be completely different. And maybe not surprisingly, but, well, I think it's surprising, right? Animals like guinea fowl, I mean, its head didn't even move, right? Like, it just kept going, right? There was like, boom, straight across. Oh, my foot just happened to go like half a leg length lower. No big deal, right? It would be very hard to achieve if you were in sort of a position control mode. You would, if your leg was going through the motions, right, you would drop down. But if it's in a force control mode, maybe. I mean, the interpretation of this it's been studied nicely. But that's the kind of thing that we want from our legged robots. Yeah. Yeah. There's a boundary for sure. Yeah. I mean, okay, if I was up here, I'm just going to go past, right? And similarly, yeah, you could certainly mess up with that strategy. It was interesting in the DARPA challenge when we were not only programming our humanoid to walk around, but we were uncertain about the terrain we were going to have to walk on, and we were trying not to fall down really, really hard. We had a walking mode that worked really, really well in lab, and it was our preferred setting. But when we got to the environment, we actually changed our settings. We called it stompy mode, okay? And it was sort of embarrassing because, like, we do a lot of work on walking robots, and you don't really want to stomp around when everybody's watching, okay? But the risk of like putting your foot into a position before you switch to force control mode, and like, if the terrain was too high and you hit something and boom, you're off, right? We didn't want to pay that price. So we just said, we'll go a little bit above our estimated terrain, like safely above, and we'll go into force control mode. And so if you watch carefully, compared to our videos in lab, the videos on the day of the competition, we were kind of like, stomping around a little bit. And I'm like, that's, but I just don't want to fall down, so I'm going to do that, right? So in that regime, I think it does pay off.
Is the DARPA challenge how BD started?
BD started well before the DARPA challenge, yeah. But they were the hardware providers for everybody who had an Atlas team, yeah. They started in the 80s as a lab at MIT, the Leg Lab, and then they left the Leg Lab and were doing simulation for a number of years. And then actually I was a student in the Leg Lab when Mark came back and said, like, we're going to start doing robots again, and could I borrow that treadmill back? And they started building robots again, yeah. Okay, so let's just think now, let's put it all together. So I'm going to use like the full, so again, we made a controller based on static analysis. Let's just think about what happens now in the full case of, let's say I'm going to just apply this controller, set a desired contact force, and start going. What happens to the box? And what I want to ask, what happens to the box if I set this force low, and then I'll sort of ramp it up. Okay, and let's just like a quick quiz. Like what do you think is going to happen? So it's in this environment. Okay. Small force. What's going to happen? I mean, great. So there's definitely going to be an impact event. If the force is basically inside that friction cone that the static friction holds, then it'll just stop. Right? In the simplest case, it'll just go, and the box won't even move. Right? If I ramp it up a little bit more, the initial impact might knock the box, but the sliding friction could slow the box down. Right? And if I push even harder, then I'll just, of course, push the box. Right? And that plays out exactly how you'd expect. So this is just a handful of different, putting that thing into the full simulation. The finger, I started it away from the box, and you see these little kinks right here. Okay, this around like 0.8 or something like this. That's when it makes contact with the box. So in the simplest case, it just goes up against the box, the smallest amount of force, and just stops. Okay. You go up a little bit more, there's an impact with the box just barely moves and then is at rest. But depending on how hard you smack into the box, you can get it to move significantly before it comes to rest. And then if you really run into it, then this is a second impact when the box slams into the wall on the far side. Okay? So even that simple controller, when you put it into the loop of a full contact, a full physics engine, it has complicated output. Is that sort of clear? Okay, but the goal, what I want to do is flip up the box. Okay, so let's do, this was just in the plane. How could I use my force control thinking to try to regulate the box? Okay, so make it flip up. So let me just put the box in some orientation like this. So this is my box frame. Okay, I'll say I'm exaggerating everything. It'll start flat, but we're going to eventually hopefully get to this sort of configuration. I've got my finger here, and I'll call that maybe the contact frame. Okay, so hopefully purple is okay, but the contact frame, by convention, there's going to be a contact frame in the frame of the robot, but there's also a contact frame from the perspective of the body. And by convention, we said that the z, positive z of the contact forces is always in the normal direction. Okay, so this is my, I'll call that frame C, and this will be my z-axis of C, CZ. This will be the x-axis of C of the contact. Okay, and let's call this other one A. I don't know, just because I have a B and a C, I'll make it A. Okay, and then this will be the z-axis here and the x-axis. Y is going into the board and is irrelevant for the planar analysis. Okay, so now we're writing the free body diagram from the perspective of the box. Okay, what do we know about, we'll assume static equilibrium again, just because that makes the board work easier, and actually it's not a bad assumption. The controller derived from the static equilibrium assumption will work pretty well even when it's moving, as long as you don't try to play tiddlywinks with it. Okay, so now we actually do want to make a moment in the box. So we're going to use not just little f, but big F. We need a full spatial force treatment. Okay, and the forces at play here are the force between the finger and the box, which is naturally described at the frame C. It's applied to body B at the point C. It's heavy, but it's needed. Otherwise, you'll get signs wrong and all kinds of stuff, okay? And especially because we're going to move all these forces to be applied around the same point. Right? So you have to remember which body they're applied to and which point they're applied to, where they're expressed in, all the things. Okay? We still have gravity. Okay? It's applied at the center of mass of B. Could write that as little b maybe if I wanted. And then I have the force coming from the ground. Okay. And the question is, what do I know about these? This is, quick mechanics sort of exercise here, but what do I know about these different forces? This one, I guess I know. It's just going to be mg. Probably have a monitor right exactly in the way there. Okay. This one's pretty simple. That's just going to be mg pointing down, expressed in the world frame. So I have to translate it to get it into the body frame. I have to manipulate it. I shouldn't say translate, because it's actually rotation. Okay. We know a few things about the forces at the friction and the force of the ground, too, right? For instance, let's pick one of them here. So the force of the finger applied to body B at point C, and if I express it in the frame C, and I take the Z element, I hate it, but okay, that's the way to write it. That component of that spatial vector is positive. What does that mean? That means the finger doesn't pull. Right? There's no suction cup there. It's only applied to apply force into the body. Is that notation okay? Yeah. All right. What else do I know? I know there's a friction cone. Okay, so the other, if I take the x component of that, then let me write even just the lowercase one of this, I guess. The magnitude of the other component is inside the friction cone, right? So there's some friction cone here. Of static friction, and that force vector has to be inside that. Of course, the same thing holds for the other one. I guess I'll use my other cone here. There's going to be some friction cone here. We know that the total force from the ground applies to the body B here is going to be represented by some force vector inside that friction cone. Right? It's in the space of the normal vector here. Okay, so it's interesting to now think, like, I want to try to rotate this thing up. So I'd like to produce a moment here without sliding here. Okay, the bigger that coefficient of friction here is, the better. Okay, and similarly, the bigger the coefficient of friction here, the better. Okay, but I need to solve for a force here that will cause that moment without sliding. If I just push naively, then I'm going to slide, like almost always. Okay, especially when you get to higher angles and stuff. Okay, so, but given the basic equations and our favorite, spatial algebra for forces, we can translate the constraints on the friction, which are simple to write in their natural frame, into a common frame. You can choose the body, you can choose this point, whichever you prefer. Okay, and now the friction cone constraints here apply. If you say I want to be inside there, that means there's a smaller range of possible contact forces that I could apply, which would not violate that friction. Okay, I wrote it out in gory detail in the notes, but it's actually just that. It's just moving these to the common frame, and then seeing what the remaining forces are allowed. And then, given those remaining forces, I'd like to try to create a moment around that body. Okay? So I did it like this. Come back to the middle here. I basically said I'd like the torque around, pick it around A, for instance, that the finger applies, but written in A. Okay. I'd like that to roughly be, let me just write it in this shorthand and then make sure you understand what I mean. So this would be a proportional integral derivative control. Okay, so I'm going to make some concept of the angle of the body. I could pick something like this. I'm going to say there's a desired angle for the body. And basically, if I'm below that angle, I want to pull up more. If I'm above that angle, I want to pull up less. And I'll use a simple linear controller to do that. Subject to the constraints that I'm in the friction cones. Yeah. You have to be careful, right? So when you translate, when you change the position, the application point of a torque, you pick up these moment terms. So I'm using the static analysis, but I'm ultimately going to actually create a non-zero moment. I want this to break equilibrium in the moment direction. Yeah. I'm not sure that's what you're asking. But I think it's not quite the same to have a moment around the body as it would be on the. In this case, intuitively they're similar, but those are going to be different numbers. You could apply. You could think about applying a torque in either case. Yep. Yes, so those are the equations to move things around. So if you're in total static equilibrium in the body, then you're also in static equilibrium here. I agree with you there. But that would move elements of the torque into the forces and vice versa, right? The relative role of moments and forces changes when you move the positions around. Yeah. Okay. So writing this sort of like a linear objective here, subject to friction cone constraints, that turns out you can write that nicely as a quadratic program. And so I coded that up here. Let me show you how it looks. All right. Here's my Cheez-It box, my planar bin. You see I sliced the edges off. I went and left it in point contact mode instead of hydroelastic for these examples, just because I want you to see the forces at particular points always. It's just actually a little easier to see it in this. And I've got my point finger here. Okay? And so what I did is I basically took this desired angle of the box, and I just put that on a slider. And if I've done the math right, then you should be able to move that slider around. And this is a full simulation that I hope is running. Oh, there we go. Okay. Okay, so it's running not very well. Anyways, I can exactly compute the forces I need to orient the box, right, at a sort of an arbitrary angle, always staying inside that friction code. Now, probably it's actually sliding a little bit, especially if I move fast. It's probably going to, yeah, let's see if I can make it move, right? But because that's my quasi-static assumption, right? But if it was perfect, if I was moving nice and slow and everything was was correct, then I've got a nice. Seems like the internet is something slow. Maybe it's just my computer. Something's really slow. Well, not as beautiful as I hoped, because like I'm trying to turn the browser and it's not updating, so it's not. Yeah, see, it was working okay. Yeah, oh, I know you believe me. Oh, see, there we go. Okay. All right, now, but here's where it goes wrong, Peters. Right, so I can that finger. Oh, dang! Then actually I got up before it fell off, but I made all these assumptions and all the calculations based on the relative location of the finger relative to the whatever. If the finger slides off, my math was just completely wrong and something goes bad. And actually, if you were to, there was another assumption that I made in the controller because there's an important point about sort of not knowing, force control is trying to be a little bit less, it should depend a little less on the geometry. That's kind of just philosophically, one of the good things about force control is to depend a little bit less. So I actually didn't assume I knew the position of the finger relative to the box. I just kind of did the math as if the finger was here or something right in the middle. And then when the finger's sliding around, I didn't update the math to reflect the different geometry. And the controller's quite robust to those. The basic idea that if I push harder, then I will go up in that direction. If I push less, I'll go down. That still works. My estimate of the friction cones might be a little bit less correct, and that's where I could get sliding if my finger moves too far from whatever estimated point. Okay, but these are pretty robust strategies. Yeah. Yeah. So I did assume that I had some estimate of theta. So I could measure theta from a perception system, or maybe if I did want to think about where my finger was or something like that. So I would just have a little strategy. Yep, exactly. There's a version of this that, I'm plugged into the internet. I'm not sure why that's not working well, but let's try one more time. Yep, you certainly could. Now my finger's wedged into the corner. Should probably restart the sim. All right, let's try one more time, but I'll do it. I wrote a little script that did roughly what you just asked. I think I did. Here we go. It's going to go until it makes contact, and then it's just going to slowly rotate up. It's autonomous. It's also open loop. Okay, I just went force, and then force. The only feedback is from this term here. Okay, to calculating the moving friction cones as a function of that angle. Okay. And it slowly, eventually turns up the box. Okay, that would have been very hard to do with position control, right? The fundamental constraint there was that this corner stays in the friction cone. If you're just a robot that's thinking about where it is in space, it'd be extremely hard to sort of regulate that quantity. This is a fundamentally sort of a force control based task. Yeah? Yeah, I would say that's a great point. I actually forgot to make it. I walked right over it. Yes, so it's relatively insensitive to the geometries, but it does depend on the estimate of the friction cone. Yeah, approximately. You could make it conservative, for instance, and then so what would happen if you made it too conservative? It might say there's no solution, that I couldn't find a force that would cause that angle without violating the friction cone, but at least it wouldn't slide outside the actual friction cone. Yeah. You need an upper bound or something. Good, okay. So I would call that strategy where you're very explicitly programming, yeah. Yep. So you could imagine asking for what's the minimum, or commanding the minimum force that would, I think that would be in competition with the objective of commanding a particular tau. You'd have to choose something slightly different. You'd say, like, I want to make some positive or some change in angle in the direction, and the one that I want to make is the one that is keeps my friction estimate as small as possible. Right? You have to pick what's a constraint and what's your objective. Your objective would be about minimizing the friction cone estimate. Mine was about treating the friction cone estimate as a constraint and trying to go as close as I could to the desired theta. Somehow, if your friction is not a constraint but becomes an objective, right? I think if you said, for instance, find me the minimum mu, right, then that's going to bring it up here. And so you need to either have those two compete or find a way to shift this down here, right? But I think it's possible. You just have to probably think of the cleanest way to write that formulation. Okay, so that general approach is called, I'd call that direct force control, where you're very explicitly trying to control the interaction forces. you have like some contact desired force, right? And you wrote a controller to try to implement that desired contact force. Not surprisingly, the other half of the literature is on indirect force control. And it's really an important philosophical difference, okay? So rather than trying to explicitly program the force, okay, the philosophy in indirect force control is that you should program the interaction. Okay, you want to program the dynamics of interaction. Okay, and I'll tell you what that means. So just so you know where we're going here, right? There's two major versions of this that we'll talk about here. One is stiffness control, and the generalization is impedance control. Okay, and the fundamental idea is don't program the force explicitly, program the way you want forces to what you want to react to forces. Okay, so let me tell you that with pictures. So a perfectly reasonable thing to do would be to think of your simple point robot here. Maybe I'll here's my robot. Let's just say I'm in free space, right? A perfectly reasonable way to command where this robot moves in free space, I could say I want to move the position to a certain point, but if I want to be a little gentler, maybe a different idea, which is just as is very powerful, okay, is let's think about having a virtual point. Virtual target here. And think about programming the interaction so that the motion of this finger, or this robot, is as if it was being pulled by a spring, probably a spring and a damper, okay, to this virtual point. Okay? So this would be sort of a spring. This is a damper being pulled to that virtual point. And then, even when contact happens, now I get some contact, I'd like the response of my finger to that contact to be as if I was still moving towards this point, but somebody knocked me, and I'm going to respond as if I was attached to a spring. Okay? So instead of trying to program force explicitly, you're going to try to program the stiffness of that spring. Okay? And the damper, generally. Yep. And that's kind of nice because where the force control, you saw the force control, there was a case where it went beautifully into when it was out of contact, it went beautifully into contact. There was also a couple of cases where it went and shut off, right? Force control is actually a pretty lousy way to control position. If your goal is to actually control position, right? It's a great way to control force. Okay, this kind of blends the two in a nice way, right? If you're not in contact, you can think about just moving this around and thinking about it like a soft position controller. Okay, but when you're in contact, you can think about that stiffness as sort of a way to program the contact force. All right, so how do we achieve that? So if I write the equations of motion of my simple point mass here, I have gravity plus whatever command force I'm putting in, plus potentially a contact force. Always in the same frames, right? But the goal is to have a system that looks like a spring mass damper system. Okay, so what you'd really like is that the equations would come out to be something you'd see in 1803 or something, you know. I'll just even do B Q dot plus K Q minus Q dot D. Okay, so you know, if this is a 0, then that looks like a spring mass damper system that has a rest length at QD. As soon as I put a force in it, it still looks like a spring. It looks like a forced spring mass damper system. Okay, the mechanics of that system are sort of easy to design. You can think about changing the stiffness, you can make it stiffer or whatever, and its you know, its response to unexpected things is well understood. Okay, in fact, you can even prove things about as long as my contact force is, like for instance, if I run a controller that establishes this invariance, then basically you can promise that your robot's not going to go unstable in the real world as long as the thing you're touching is not actively antagonistically trying to confuse you. But these kind of controllers, you know, if you think about just having a spring mass, when you bump into things in the world, nothing's going to go crazy and go unstable. There's a whole theory of passivity theory, or more generally Port-Hamiltonian theory, that talks about promising that this, as long as it interacts with a passive environment, or you know, you can make relatively benign assumptions about the environment and say that these controllers will never do something crazy. So, and that's actually been important. Like if you want to, some of you know the Franka-Panda robot, for instance, like and even EWA before that. They have safety cases that they've built that say that those are safe to work around humans, based on proofs that are based on the sort of passivity theory and the passive properties of their controllers. Okay, so if we can choose a U that achieves this, this is called stiffness control. Okay, make your robot act like it's a spring mass damper. Okay. Now it's not too hard to figure out what the U needs to be to control that, right? You have to cancel out gravity. And then add in something which actually looks exactly like a PID controller or a PD controller that we've seen before. Minus B Q dot. Okay, so this is often called gravity compensation. And this just looks like a standard PD controller. But if you put that U into this equation, then it results in the dynamics having an interpretation like a spring mass damper system. Yeah? Say the mass is the mass of the finger, yes? Ah, good. This is not actually a wall yet. It could be, but this is a virtual point. So I think my animation will make that clear. Okay, so hopefully it runs better. Okay, so now I have a finger, which I put in pink still, but I also have a virtual finger. Okay, so my controller is one step removed from the actual position of the red finger. I'm going to pull around a virtual finger, and that's what I'm trying to draw here. Maybe I should have drawn it as just a virtual finger over here. And I could have probably color matched if I had been really good. I didn't. Okay, but so just think about a virtual finger that doesn't exist in reality. It only exists in the middle of my control logic. Okay, but I can draw it here for illustration purposes. And if I move that around, then it gets interesting when I start, running into things, right? Now the depth of that virtual finger penetrating corresponds to the interaction forces that I'm getting. Yeah. So, okay, this is great. So it is PD control here, plus a gravity compensation. The differences start to emerge more dramatically when you're doing it in the joint space of an arm, okay? But that's actually, I hope that's satisfying, that actually it's almost just PD control. The important application difference is that oftentimes PD control, you pick very high K, very high B, for instance, or well, square root of 10 less than whatever than this, okay? So proportionally smaller B that makes that critically damped. But those have to be big numbers. If you take the gravity out, if you subtract away gravity, then you can tend to make these numbers much smaller. So the algebraic difference between PID control is small, but the application difference is large, because you often are picking stiff PD gains just to fight against gravity. Okay? If you cancel out the gravity, then you can make it nice and soft. Yeah? So that's a great question. Can I remove the gravity and use a PID controller instead? That will not do as well for a couple different reasons. In particular, for instance, what would happen if I did this with a PID controller, right? So if I had an integral term in there, then basically any error that was between my virtual finger and the actual, it will basically keep ramping up the forces, trying to squish that error. So if I was running a PID controller, this arrow would just get bigger and bigger and bigger until my simulation crashed. The red makes it look angry? Or? Yeah, both. Yes, that's true. Good question, though. Okay, so here is maybe the biggest point of the lecture, okay? It turns out that programming the stiffness is an extremely intuitive way to do some interesting contact tasks, okay? So this can be like, if you change your mindset, instead of controlling the position of the finger, instead of controlling the force directly, you're controlling the interaction. Okay, then the strategy you might take to control interesting robots can just be different. So watch how easy I can make this box flip up. I'm going to cheat. I'm going to push it all the way to the side here, but all I'm going to do is push this to the side. I've just moved my finger to the inside. And now what I want to do, let me show it to you first, and then we'll just make sure it makes sense on the board. I'm just going to lift my virtual finger up. Okay? It's like I've got a spring, remember, connecting my real finger to my virtual finger. If that spring is in the right location, then not only is it going to cause the thing to rotate up, but once it gets up, it's going to do exactly the right thing and come to rest. Right? Instead of programming a force that had to somehow change very quickly once you get to the top, you've programmed a stiffness which just naturally is doing the right thing. Yeah? I can even take it back down. At some point, yeah, it's just a very robust interface. In fact, even the fact that I have this teleop interface, I didn't make a teleop interface for force. That'd be crazy, right? It'd just be, jumping all over the place. But it's a very natural way to move this thing around. Okay? Solving contact tasks. I want to bring it back down, no big deal. I just move the spring down here. I want to move it back up. Very, very natural interaction. Right? So just to make sure you see what's happening there, right? So in this configuration, if I get another color here, okay. If I think about pulling myself with a virtual spring like this, right? Then effectively, if that spring is past here, right? Then I'm going to start getting a moment around this point, okay? But as soon as I get up to this near upright configuration, that point hasn't moved. My finger did move, and it's just going to pull me around and change into exactly the second mode that I want and pull me into place. I have What's that? The friction cones? So I am not explicitly reasoning about the friction cones anymore in this. Right? That's an important point. I also didn't I didn't solve the harder task of staying inside that friction cone explicitly. You could have implied those same constraints, put that on as a constraint on my virtual finger location, right? But this one is just so elegant that I emphasize this one instead. Look at that, I can do it here. Whoops. Now you've challenged me. Look at that. Oh, no, come on. Pretty close. I'm sure I could write a controller in 5 minutes that would do it, right? And by the way, you can just make that, again, an open loop trajectory here. So if I do teleop false, this is badly tuned, but it sort of shows the fact that I didn't tune it and it still works great is maybe a sign of that it's a very natural way to program these things. Okay, anybody know the difference between this and impedance control? They're actually very similar. The impedance control, I think, maybe somehow popularized stiffness control. Stiffness control came first, but the impedance control told this story about programming the interaction extremely clearly and got a lot of people thinking in this way. So, and I'm almost embarrassed because, again, everything is like super simple in the point finger case, and it's more rich in the full multi-body case, but that's also why I wanted to do it, okay? So this is stiffness control because I had the original mass of the finger, and I programmed the interaction by programming the stiffness, but I left the mass to be the mass of the finger. I could ask for this to act like a different mass. I could try to program the inertia as well as the stiffness and the damping. Okay, and if you program all three, the stiffness, damping, and inertial terms, those triplets are basically, that's the impedance, the full impedance. Okay, so if you choose to try to reshape M, then that's impedance control. In this case, it's just the mass. Okay. Now it's interesting. People don't do that very often. So it's relatively easy to make yourself look. Let me see if I get it right. I think it's relatively easy to make yourself look heavier. Pretty hard to make yourself look lighter. A lot of times you'd like to act like your robot should be lighter than it actually is. Okay, but that requires a lot of bandwidth, typically. So one of the famous cases of impedance control is actually in the IWA. In our IWA, they reshape the rotor inertia, but they don't actually reshape the link inertia because that would exceed the bandwidth requirements. But they can do some amount of reshaping of the rotor inertia in a local feedback control. Okay. But I think impedance control is much more famous, but I actually think most instances that you'll find are actually closer to stiffness control. In fact, outside the rotor sort of case, I think the IWA controller is better interpreted. Like if you want to simulate the IWA and you're not simulating all the rotor mechanics, you probably are simulating a stiffness controller. It would be a more faithful simulation. Yeah? Yes?
So what you're actually changing is not the mass, but like the delta between the mass and the desired mass. Because it's gonna like, because the equation above is gonna subtract the mass. And like here, if you set the mass, then it's gonna cancel out the
This is a really good question. So let's just say this is the mass of the robot. This is my mass desired. Okay. How do I pick U to impose this? The first thing you might try to do would be to add in this term and subtract, or add in, basically subtract out this term, make that go disappear, and then add in this term. But that would require measurements of joint accelerations, which people typically fear. They tend to be, you would tend to say that I get positions very cleanly, I get velocities very cleanly, but accelerations, don't put that in a high bandwidth feedback controller. It's too jittery, and especially the sensitivity of jitter in that estimate to that controller would be high. So there are ways to implement the impedance control shaping that don't use direct estimates of acceleration. And that's, if you dig into the impedance control literature, those are the kind of things that you have to get right in order to successfully implement, is to try to do minimal sensing requirements. Yeah. Cool. I think maybe I'll stop there instead of jumping into the next thing with a few minutes left. Yeah, let's do that. Okay. So I hope that landed, right? Force control can be can do things that you can't do in position control mode, and programming the interaction can be way better. I mean, that's true if you're a human programmer, if you're a learning controller in RL, if you're running behavior cloning, whatever. This can be a much more natural, for some tasks, way to program. Good. See you next time.